Hey everybody, so in this video I want to first do a little review of orthogonal projections and then take a look at some of the more recent material that we've been looking at, which are looking at least square solutions. We'll take a look at different methods that we can use to solve the least square problem. So first let's consider matrix A, which is a 4x3 matrix. The first column is 1, 1, 0, minus 1. The second column is 1, 0, 1, 1. And the third column is 0, minus 1, 1, minus 1. And let's consider vector B in R4, which is 2, 5, 6, 6. And we want to find the orthogonal projection of this vector B onto the column space of matrix A. So what would that look like? So the first thing to note is that the columns of matrix A are all linearly independent and they're all orthogonal to each other. So we already have an orthogonal basis for the column space of A, namely here's vector 1, here's vector 2, and here is vector 3. And so now that we have an orthogonal basis for the column space, we have a nice formula for finding the orthogonal projection of B onto the subspace, which is the column space of A. So we have a nice formula for finding the weights that we need to take linear combinations of these column vectors, which give us the projection of B into this column space. And this is going to give us the best approximation for this vector B that sits in the column space of matrix A. And so the calculations are done in the Google Colab notebook, which is linked below in the description of this video. But you can go through these dot products. They are not too bad to check. And you can see that the first weight is going to give you 1/3. The second weight is going to be 14/3. And the third weight is going to be minus 5/3. So taking 1/3 times A1 plus 14/3 times A2 plus minus 5/3 times A3 gives us a vector of 5, 2, 3, and 6. And this is telling me the best approximation for the original vector B that is in the column space of matrix A. And moreover, we can see what are the coefficients, the weights, in some sense the betas, that I would use to combine the column vectors of matrix A in order to get this best prediction. So we'll see how these coefficients might relate to solving a least squares problem on the next slide. Okay, so we are working with the same 4x3 matrix A from the previous slide and the same vector B from the previous slide, which was 2, 5, 6, 6. And now the question is saying, well, let's find the least squares solution to the equation AX is equal to B. So here the solution is going to be values for this vector X. So let's just recall what that solution looks like. Since matrix A has all linearly independent column vectors, that means the product A transpose times A is going to be invertible. And then the least squares solution, X hat, is going to equal A transpose A inverse times A transpose times B. And we have all of this information given to us, so we can plug this all together. Here's A transpose, here's matrix A. I'm going to take this product, take the inverse of it, multiply by A transpose, and then B. So this is quite a long calculation. And you can imagine if A is some model matrix and you have like 10,000 observations, then your matrix has 10,000 rows. And this takes an extremely long time to calculate, and it's going to be really expensive to calculate that. For this smaller case, it's not too bad. And we can find that the least squares solution, X hat, is equal to 1/3, 14/3, minus 5/3. And these were exactly the same weights that we found when we were finding the projection of this vector B into the column space of matrix A. And one last slide to go through. I want to just show what this calculation would look like if instead we use the Qr decomposition. So here we've got a really messy product that we would need to compute. And I just want to compare this solution to how computationally heavy the solution would be if we used a QR decomposition. Okay, so we want to solve this same least squares problem where we've got this 4x3 matrix A that we've been working with, and this column vector B in R4, which is 2, 5, 6, 6. And we found the least squares solution using those normal equations. But now I want to take a look at what happens if we use a QR factorization for the model matrix A. And here I've done the QR decomposition, and you can check all of these calculations in the Colab notebook linked in the description of this video. But I would go through Gram-Schmidt process to find an orthogonal basis for the column space, and then we would normalize each of those columns to get an orthonormal basis for the column space of A. So this matrix Q consists of columns that are orthogonal with each other. They all have length 1, and these vectors span the same space as the original column vectors of matrix A. And then we can find matrix R by taking Q transpose times A, and then we get an upper triangular matrix. In this case, the matrix happens to be diagonal. And now we can use this nice shortcut with the QR decomposition factorization that the least square solution x hat is going to equal R inverse times Q transpose times B. And that product is over here. And first of all, finding the inverse of R is quite simple computationally when R is a diagonal matrix like this one. It's not too bad when it's an upper triangular matrix. But now the solution is taking a diagonal matrix times Q transpose times B. And if we had a huge matrix, this product would save us tons of effort and computational time to derive the solution, which in the end we get as 1/3, 14/3 minus 5/3. This is consistent with the previous method that we used that did not rely on the QR factorization. So these methods both give us consistent solutions. That's great when we have different options available to us for solving problems. In particular, when matrix A, when we're given the QR factorization of matrix A, so if you were given this information, then it's certainly way easier to calculate the solution using the QR factorization. If you don't know what the QR factorization is, then you might just go straight ahead using the normal equations to find x hat. I'll let you decide which method you prefer.